Assalamu alaikum everybody. I'm very good time for you all. With you is Abdulfattah, your classmate at Dr. Azrin class Advanced Data Structure. In this demonstration I will talk about AVL trees. First of all, we will talk about basic information about AVL trees. What are they? An AVL tree is a kind of binary search tree, and we know what are binary search trees, but with a more advanced condition related to the balancing of the tree, and we will talk about this condition in the coming slides. AVL is named after its inventors Adelson, Velsky and Landis. A, V and L. AVL tree approximates the ideal tree, completely balanced tree. So we can also call this kind of trees as balanced trees, because after any addition or deletion of any node to the tree, we must maintain the balance of the tree. So AVL tree maintains a height close to the minimum, as we can see in the next coming slides. Definition: an AVL tree is a binary search tree such that for any node in the tree, the height of the left and the right subtrees can differ by at most 1. So for every node we must calculate the height and the height of the left subtree and also the height of the right subtree, and calculate the difference. If it's more than 1, we say that it's not an AVL tree, meaning that the difference is either 0, 1 or minus 1. If it's, for example, 2, 3 or minus 2, minus 3, it will not be an AVL tree because it's not balanced. Balanced trees. Here we have 2 trees. In the left side of the screen is a balanced tree, in the right side of the screen it's not balanced. Here, for example, if we take this node, we will see that the height of the right subtree is 1 and the height of the left subtree is 2, and the difference is 1 minus 2, which is minus 1. It's okay. If we take the root, the height of the right side is 2 and the height of the left side is 1, 2, 3. So 2 minus 3 is 1 or minus 1. It's okay. But in the case of the right side tree, if we take, for example, 8, the height of the right subtree is 1 and the height of the left subtree is 3. 1 minus 3 is minus 2. So it's not balanced. Also, if we take 12, the height of the right side is 2 and the height of the left side is 1, 2, 3, 4. 2 minus 4 is minus 2, so it's not balanced. There are some properties of AVL tree. The depth of a typical node in an AVL tree is very close to the optimal log n. Consequently, all searching operations in an AVL tree have logarithmic worst case bounds. An update, either insert or remove in an AVL tree, could destroy the balance. So it must then be rebalanced before the operation can be considered complete. So after any insertion or removal of any node to an AVL tree, we must test for balancing of the tree. And this is the key point in this kind of trees: balance. What do you mean by rebalancing? Suppose the node to be rebalanced is x. There are 4 cases that we might have to fix. 2 are the mirror images of the other 2. So actually we have only 2. The first case is an insertion in the left subtree of the left child of x. Left. And the second case is an insertion in the right subtree of the left child of x. Right, left. And the third case is an insertion of left subtree of the right child of x. Left, right. And the last case is an insertion in the right subtree of the right child of x. Right, right. The first and the fourth cases follow a pattern called zigzag. Left, left, zigzag, or right, right, zigzag. Whereas the second and the third cases follow a pattern called zigzag. Zigzag, right, left, zigzag, left, right. Balance is restored by tree rotations. So, to rebalance the tree, we need to do some kind of rotation. Case 1 and case 4 are symmetric and require the same operation for balance, which is single rotation in these 2 cases. Whereas in the second case and the third case, they are symmetric also, and they require the same operation for balance, which is the double rotation. We will talk first about single rotation. What do you mean by that? A single rotation switches the roles of the parent and the child while maintaining the search order. Meaning that we rotate between a node and its child. So child becomes parent and parent becomes right child in case 1 and left child in case 4. The result is a binary search tree that satisfies the AVL property. In the first case, we do a right rotation. Here we have a tree before rotation, which of kind left, left, zigzag, and we do a right rotation to it. In this kind of rotation, we just change the rules between key 1 and key 2. So key 1 becomes the parent and key 2 becomes the child, and it takes the right subtree of key 1, so it becomes the left tree of key 2. Again, key 1 becomes the parent, key 2 becomes the child, and B, which is the right subtree of key 1, becomes the left subtree of key 2. For the fourth case, it's a symmetric operation, but we do a rotation to the left. Here we have a right zigzag pattern, so we need to do a rotation to the left, and we do that by making key 2 as a parent of key 1, and B and subtree B, which is the left subtree of key 2, becomes the right subtree of key 1, and that's it. Now we move to a visualization of single rotation. Okay, we will continue with this demonstration of AVL tree by using this applet which visualize the operations of an AVL tree. This applet contains the many methods of AVL tree like insert, find, delete, and delete all. Also traverse in any strategy of traversal, in order, pre-order, post-order, and so many. We will check the options step by step and build up our own tree. We will first add the node 12. It will be the root node. the tree now is balanced, we will add then 8. It will be added to the left side because it's less than 12 and the tree is balanced. And now add 6. It will goes, at 16. It will goes right because it's more than 12. If we add more nodes, for example 4, it will be added to the left because it's less than 8. The tree is balanced, still balanced. If we add one more node, which is 10 for example, it will goes left, then goes right because it's greater than 8 and the tree is still balanced. If I add 14, it goes right because it's greater than 12 and then goes left because it's less than 16 and the tree is still balanced. Okay, I will add up 2 more nodes here. For example 2, it will goes left, then left, then left, and the tree is still balanced. Okay, if we add 6, it will goes left, then left, then right because it's greater than 4. If we examine the balance, this subtree is balanced. Also the whole tree is balanced. What happens if we add another more node which contains the value 1, for example? Insert 1 is less than 12 goes left, it's less than 8 goes left, it's also less than 4 goes left, also it's less than 2 goes left. If we examine the balancing of this tree, we will see that this subtree is balanced, also this subtree is balanced, but this subtree is not balanced because the height of the right subtree is 1 and the height of the left subtree is 1, 2, 3. The difference is 1 minus 3, which is minus 2. So we need to do some kind of rotation to maintain the balance of this AVL tree. What kind of rotation must we do? We must first examine what pattern do we have. Here we have the pattern zig zig, so we need to do, or left, we need to do one single rotation to the right. Just change the rules of 4 and 8, so the node 4 will be the parent and the 8 node will be the parent, and takes the right child of 4 as its left child, as I will show you now. So 4 becomes the parent and 8 becomes the child, and 6 was the left child of 4 and now it's was the right child of 4 and now it's the left child of 8. If we examine the balancing, now the tree is balanced. Okay, now we move to the second kind of rotation, which is double rotation. A single rotation that we discussed before does not fix the inside cases 2 and 3. So in these 2 cases it is required to do another kind of rotation, which is called double rotation. This operation involves 3 nodes and 4 subtrees. Single rotation is not suitable for case 2 and case 3, as we will see in this example. Here the pattern is zigzag because the internal subtree is taller than the external subtrees, so single rotation is not suitable. but if we apply it, we can see that it's not suitable. If we do one single rotation, we will make key 1 as a parent and key 2 as its child, and Q, which was the right subtree of key 1, as the left subtree of key 2. And now if we examine the balance of the tree, we see that it's still not balanced. So we need to do left and right double rotation to fix this case. This is an example. Before rotation, we have an internal subtree which is taller than the external subtrees. So here we have a zigzag pattern, so it's not suitable to do only one rotation. We need to do two rotations, left and then right. The first rotation takes place between key 1 and key 2, and the second rotation takes place between key 2 and key 3. Okay, in the first rotation, key 2 becomes the parent of key 1, and key 1 takes the left subtree of key 2 as its right subtree. And in the second rotation, key 2 becomes the parent of key 3, and key 3 takes the right subtree of key 2 as its left subtree. Now we move to a visualization of this case. Okay, now in this second part of demonstration of AVL, I will show you how to do the double rotation. If we add 5 to this tree, it will goes to the left of the node 6. And now if we test the balance of the tree, we will see that this subtree is balanced, also this subtree and this subtree. But if we go upward to the node or to the root of this whole tree, which is 12, we will see it's not balanced, because the height of the right subtree is 2 and the height of the left subtree is 1, 2, 3, 4. 2 minus 4 is minus 2, so this tree is not balanced. What kind of rotation must we do to maintain the balance of the tree? Here we need to do double rotation, because we have a pattern of left, right, zigzag. This zigzag pattern forces us to do double rotation. In double rotation, we do the following. This node becomes the parent of this node and this node, and the left subtree of this node will be the right subtree of this node, and the right subtree of this node will be the left subtree of this node. So this is the first rotation, and this is the second rotation, and now the tree becomes balanced. Okay, brothers and sisters, I have came to the end of this demonstration of AVL trees, and I hope that you find the benefit of it. Thank you very much for you all, and see you in the next demonstration of splay tree.